Good morning. This is Chrysalide Electronics. I'm working on this schematic for power supply. This schematic is actually final and working, has been tested. And this is part of a series of explanations on the design and as well as ebooks, both freeware and low price tutorials that I will provide. Let's get into this schematic right now. This is the final board layout where we see the 7-volt rail, 5-volt rail, ground, test points, various components. First thing, what do we call a rail? A voltage rail is simply a potential available on the board, be 5 volt to 3.3 volt, 7 volt or something. On this board, the ground plane is laid up on bottom, and we have a 7 volt rail available on top. There is an advantage of laying the ground plane on top instead of on bottom, since most components use ground when we have lots of CMS components, surface mounted components. Usually it's easier to have a ground plate. It's very practical to have a ground plate on top so that we have a ground in many places and we can use it for our components. And also have a power supply rail on the bottom is also very practical for laying up the PCB. This board is a simple two-layer design. We can see the schematics on the left hand and the PCB layout on the right hand. Looking at the power supply design, we have the jack power supply inlet. It's designed for 7 to 16 volts actually, according to this MT2492. And we have two stages of power supply in this very simple design. I laid out the buck over here and the regulator over here. What is a buck? It starts from say 7 to 15 volts DC, and it uses an inductor and an oscillator inside, and it's chopping up voltage input, and basically that's a filter. It has feedback loop and capacitors to properly stabilize the output voltage, and we have 22 microfarad on input and output capacitors. And a buck converter is quite efficient. Say, for example, it can be 90% or 95% efficiency. The disadvantage of it is that there is an oscillation imposed on DC output. So there the design is 7 volts. According to these resistors, we can have 7.1 or 2 volt, for example, plus minus 100 millivolts. And the oscillation will be filtered on the later stage. So we use this first stage to get the external power supply down to a voltage we can manage. And this is 7 volt plus minus 100 millivolt, for example, not stabilized. Then we use a linear regulator LM7805, which is not efficient. It's actually internally transistors, so it makes basically losses. So say you have 1 amp in and you need 1 amp out. You have the same current on each side, but you have, for example, 7 volts on the input and 5 volts on the output. And basically it drops up the voltage across its own terminals. Therefore, it's a lossy device. It's only making loss, heat loss out of the voltage it wants to stabilize, so the efficiency is not great. And the lower the voltage drop, the best for the component, less heat and better efficiency. So we don't want, for example, to get from 12 or 15 or 24 volts down to 5 volt or 3.2 volt with only this component. It can be used for very low current, but when we have, for example, 100 milliamps or more, usually we want a buck when we get from high voltage to low voltage. Typical rails are 3.3 volt and 5 volts on the output for most of the components we can use in electronics at this simple design stage. We have then the test points, the mounting holes. The fiducials are used to properly print the PCB and make PCB aid assembly at the line, production line. We have shunts for current. We want to put any switch or current measurement resistor in there. Jacks for the output and headers for the connections. This is the buck microchip from Aruiduino MT2492 and the STM L78M05, just a linear regulator. We see from the datasheet of the buck converter that we can get from 4.5 to 16 volts. And when we get 4.5 volts input, the output will be lower. So in the design, I put here that 7 volts will be the minimum input voltage if we want to properly regulate down to 5 volts on the output. We have efficiency up to 96%, as I stated, and 600 kilohertz frequency, operation frequency. And the features of this particular chip with protections over current and current limit. It's a SOT23, so surface mount package. And we see the typical wiring diagrams with 110 and 15K for their example. And the typical efficiency over here. So basically from 93 to 96%. And we see the 22 microfarad input-output capacitors, ceramic 22 pico. The resistors will adjust the output voltage. And we have the inductor because the high frequency switch, and it will regulate the output voltage through the inductor and the capacitor filter. We see the absolute maximum ratings. We don't want ever to exceed 70 volt or minus 0.3 volt. Thermal resistance is 170 degrees per watt, but we are using it for roller consumption in this case. And we see the layout over here. We have this floating voltage connected to pin 1. We see this pin 1 over here. Another ground pin. We're using the ground plane. The adjustable feedback, the enable. We connect the enable to plus. The chip is always enable. Power supply input, switching pin, which is the output. We see the nominal rating over here. We see the switching frequency, 600 kilohertz. Typical characteristics and the regulation, and we see that the voltage output, for example, at 5 volts, will get from 512 down to 510 according to the load. It can vary a bit also according to external components. And we see the regulation waveform. And we don't want it to supply directly microcontrollers or sensitive loads. If we want a very good stabilized design behind this chip, we will use a linear regulator as a second stage. Internal function block and a description of the circuit. It has a soft start to prevent overshooting during startup. It has an internal regulator and protections. And this is the formula to calculate the output voltage, the formula to calculate the capacitor, and what we get in terms of filtering. The inductor 4.7 to 22 microhenry, and recommended layout. So we see that the power plane are thick, and the components need to be laid close proximity to the circuit, to the chip. That's almost all for this buck converter. Linear regulator L78M, it's a TO220 like this, and available so in a surface mount, 500 milliamp, and we are using 5 volts output. It has a short circuit protection and thermal overload protection. Has a starting circuit, uses an internal reference voltage. The internal circuit looks like this. This is symbolic. There are certainly some variants inside that we don't see here. And it's supposed to work from up to 35 volt input or 40 volt input and regulate depending on the selected type from 5 to 18 volt. And is just a 3-pin device, very easy to use. We have 0.23 micro and 0.1 at the output for bypass. So that's the power supply, local power supply, to avoid the inductance effect on the long line. A couple recommended circuits and the characteristics, and we are using the 5 volt. We see that it's stabilized with 62 dB, essentially independently from the line side voltage fluctuations. We have a good stabilized output, little noise. test parameters, different types. This is a 06 version, 08, 12, 15, 24. Our version looks like this. This is the 05. We have 4.8 to 5.2 volts. It will be very close from the typical value, specifically at 25 degrees C. A couple curves over here, according to various temperature. We see about 1 volt of dropout, so we need 1 volt more on the input. And we are using 7 volts at the input and 5 volts at the output. We allow 2 volts for the regulation of dropout, minimum. We have the voltage rejection with frequency. So that's a noise characteristic, essentially. And transient characteristics. And couple informations. Very simple to implement. Two capacitors, the circuit. They recommend tantalum, Millar, and low ESR capacitors closely mounted to the circuit and minimize the ground loop. That's also for EMI or EMC considerations. They have the different schematics. If we want to use at a different voltage over here, adjustable voltage with a regulation and a potentiometer. If we want to amplify the current, we are using an external PNP transistor. When we have a very high input voltage, we can protect the circuit. And this is with a temperature compensation, which needs to be trimmed to be accurate. Package informations, ordering informations, output voltage. So that's a two-stage buck and linear regulator power supply. The fiducials are for the PCB manufacturer when we will order with the components. The components are set up properly with the footprint packages set up for every component. When we have finished implementing schematics and going into the layout design, we have something like that with our big capacitors, 22 microfarad, injector over here, buck over here, capacitors as needed, and then the second stage is 5 volt regulation, capacitors over here, and then we have some magic over here, like this shunt to measure the current or install a fuse or protection. The output terminals or jacks, input jack. We don't have any input protection in terms of over voltage, short circuit fuse or something. And that's all for this power supply design. I will continue posting various designs, and some of them will be shared for free. Some of them will be shared as tutorials and with ebooks. And some of them will be available for low price with the schematics and the ebook for people who want to pick up this design, which were properly tested and validated in the test lab over here, and eventually use them in your own project. The Kicad are fully implemented with the part selected, footprint, part type, and the LCSC reference as well, so that they can be exported and placed as a purchase order for manufacturers straight from the export tool within Kicad. Thanks and day to all.